Euler's method, part 2. Examples. Suppose that y is a function of x, but that we don't necessarily know what the function is itself. But we do know the slope dy dx equals xy plus y squared, and that y at 0 equals 1. Using Euler's method, we want to approximate f of 1 using a step size, a delta x of 1/2. That is, we're going to use 2 iterations of Euler's method to get from x equals 0 to x equals 1. Recall that Euler's method is simply writing repeated tangent line equations, where I like to use point-slope form of the line and then modify it to make it a little bit easier for me to work with. First thing I would do is I would add the y1 over, y1 being the starting point or the starting y value, and then changing x minus x1 to delta x. So, Euler's method, writing lines, we know that we need a slope and a point to write the equation of any line, and we have both of those things. So I like to write the information down over here. My starting value is 0, 1. The slope is xy plus y squared. So plugging in, I get 0 times 1 plus 1 squared gives me a slope of 1 at the point 0, 1. So I can now plug this information into my equation over here. So the tangent line, 1/2 of an x, if you would, away from my starting x of 0, that is, the tangent line at 1/2 is approximately the function value at x equals 1/2, which is given by my starting y value plus my slope times the given delta x above. So the tangent line at x equals 1/2 is 3/2, which means the approximation for my function value at x equals 1/2 is 3/2 as well. This gives me a new starting point, the point 1/2, 3/2. We can find the slope at that point, which is x times y plus y squared, which gives me 3/4 plus 9/4, which simplifies down to 3. So now I can use this new starting point and the slope at that point and write the equation of the tangent line there. And we're going to use that to find the y, or approximate the function value, 1/2 away from my starting x value. That is, we're going to approximate the function value at x equals 1, which is my starting y, plus my slope times delta x. So 3/2 plus 3/2 is 3. So the function value at 1, using 2 iterations of Euler's method, gives me that the function is approximately equal to 3. Let's take a look at one more example down here. Again, I have a function, but I don't know what the function actually equals. But I do know the slope dy dx at any point, and I know a starting value, f of 1 equals 1. Using 2 iterations of equal size, we're going to use Euler's method to approximate f of 3. So let's take our starting point. Let's find the slope at that starting point. So 2 times 1 over 1 minus a half gives us 3 halves. And we can write the equation of the line using that point and that slope. So I'll write this out again so we can see it. This is the form of the line that I like to use. And since I know y at x equals 1, I want to find the y value or the function value at x equals 3 using 2 equal iterations. That must mean that my delta x equals 1. So y at 2, which is 1 away from my starting x value, is my starting y value plus the slope times delta x. Which gives me that y of 2 is 5 halves, which is the approximation for f of 2. I have a new starting value. It's the point 2 comma 5 halves. We can find the slope at that point. So I have 2 times x over y minus x over 2. And let's simplify this one over here. So I have 4 divided by 5 halves, or 4 times 2 fifths, minus 1, which is 8 fifths minus 5 fifths, or 3 fifths. So now I can find the tangent line value at 2 plus delta x, which is my starting y value plus the slope times delta x. And if we were to simplify this one, I would have 25 tenths plus 6 tenths equals 31 over 10, which is the approximation for my function value at x equals 3.